Today I'd like to talk to you about the MATS mission. MATS, I didn't write it out because it's a sort of weird acronym. It's mesospheric aerosol and airglow tomography and spectroscopy for some reason. Originally it was mesospheric airglow transient signatures, but it got changed. Anyway, the MATS instrument is PI, is your gimbal, so I'm actually giving this talk on behalf of the MATS team today. Your gimbal is the PI, is at Stockholm University. Linda Megner and Ola Martin Christensen have been working as the project managers, but also on the science and the instrument work. Nikolai Ivanchenko is at KTH, is the other university in Stockholm, the Royal College of Technology, and Björn Lind is one of the PhD students in Stockholm. The KTH made the CCD readout stuff. And then we have, of course, the people at PEDFOR, which is the Swedish Space Agency, and the industry partners that built both the spacecraft, which is OHB and OAC, and SIS Instruments that built the instrument. And we had a lot of help on the freeform optics from the Kyunghee University in Korea. So I shouldn't forget to mention them. They're very easy to forget, so that's why I wanted to actually remember them. Okay, so MATS. It's a Swedish satellite, small satellite. It's actually smaller than this. It's about the size of the box on the bottom here. And the panels are not there. The back of it is the solar panel, just to give you a feeling for the size of it. It was supposed to be a fast, quick, cheap satellite, and it took a little bit longer than expected, like everything. So it was started in 2015 and finally launched in 2022, having spent a year in a box because of political things in the world. And it was a bad year in a box when we could have been doing nice things to it, but never worry. It's designed to look at waves in the atmosphere, gravity waves, and it's using two tracers to do that. One is the oxygen A bland airglow, both night glow and day glow, and the other one is knocked loose in clouds in the polar summer hemisphere. This is where we're supposed to launch, but because of nice things on the this is just to show you the launch when we got sent up finally from New Zealand on an Electron rocket on, what was it, the 2nd of November. It was supposed to be All Saints Day, and because of the time difference, we went one day wrong. And finally there will be a little picture coming up here when they, actually live video, we could see when they ejected the satellite from the carrier. So this is when it went up into space. It was very nice, all went very well, got signals fairly quickly afterwards. Back to the presentation. Start from the current slide. Why will it not go? What's wrong? Oh, there it is. Okay, it's here. It was the second one. Okay, so why MATS? Why do we build this satellite? Well, this is a picture from Preuss and JGR in 2008, looking at what can we see in terms of gravity waves from the current instruments that are in operation at that time. And these are the horizontal wavelengths, and these are the vertical wavelengths. These are the propagating gravity waves and their propagation angles roughly. And this is what you can see in the nadir. You can see vertical wavelengths down at best 20 kilometers or so. In the limb you can see a little bit better. And microwaves you can see sort of this green area here. But there's a block that is missing, and that is this region here where you have horizontal wavelengths of the order of 10 to 100 kilometers and vertical wavelengths between 2 and 20 kilometers or so. So the idea of MATS was to try to fill part of this gap as well as we could. And as I said, we are using two phenomena in the atmosphere. One is the oxygen airglow at 762 nanometers. And this is just a picture from the VIRS instrument looking in the nadir, where you can see gravity waves in the airglow propagating out from a center here. And this is a picture of, oh, I shouldn't move away from the microphone. This is a picture of the knock-loose clouds where you can see lots of wave structures in them. And we have 2 channels on the instrument at 275 and 305 nanometers to help us look at those, and also to get some size, particle size information from the 2 wavelengths. So what do we have in total? This is a picture of Mats. We have a limb camera, which has in total 6 channels. So we have 2 UV channels that are meant for the NLC, or the knock-loose cloud observations. So they're only used in the northern hemisphere and southern hemisphere summers. So they should be on right now, well, beginning the NLC season in the northern hemisphere. And 4 near-infrared channels, 2 centered on the 7620 nanometer, 7620 angstrom, or 762 nanometer. I'm still old school, I still use angstrom. 762 nanometer air glow, and 2 on the side to give us the background. So let's see. Oh yes, and in addition we have a nadir camera here, which is again looking at the air glow, the 7620 nanometer. And it's designed to have the same swath width as the limb images. And these, now we should go here. Oh, so now I'll tell you a bit about this. So this is the instrument, the limb instrument. So it's built using free off-axis 3-meter reflective system with adjusted to have no astigmatism and as little as possible distortions in it. The mirrors are actually free-form, so they're not spherical mirrors, which meant they were specifically designed and modified to give us the best possible imaging qualities we could achieve here. The field of view of the instrument, if we use the whole CCD, is about 250 by 40 kilometers, yes. And it's about a 10 square centimeter entrance. And very important is this baffle in order to restrict the stray light. And it's actually been coated with nano particle carbon Vanta black substance, which was really black. Yeah. And it seems to have done a nice job here. So we have the main beam coming in here off the main mirror, secondary mirror, and then into a series of beam splitters and filters that allow us to split out the different channels. So this splits off the UV here down into the UV channel. One of them is on axis and one is out to the side here through a beam splitter and the 2 filters. Here we have the infrared. This is the one on band. This is one of the off band ones, and the other 2 are sticking out the back there that you can't really see through these beam splitters that are putting half the energy into the other direction, or approximately half the energy. Right. Just as I said, we have the 4 channels on the infrared. 2 of them, the orange line here and the green line, are put on the main emission here. And the idea is that the narrow band one picks up the center of the thing, the wide band one picks up the whole band, and as the temperature of the emission changes, the band will expand and decrease, and by taking the ratio of the full band to the narrow band, we can get a measure of the emission temperature. The idea is to do this on the final sort of volume emission product rather than on the line of sight, although you can try to do that as well. Okay, so this is going to be another movie, which means I'll have to switch it, but this is good because I can show you what to look for beforehand. So up here you're going to see raw data, so purely raw counts from the CCD on the IR1, the infrared channel centered on the A band, so the narrow band channel actually. Exposure time's about 5 seconds, and we're going to go through a couple of orbits here. Down here you can see where we are. So we're going to, the satellite is the red dot, if you can see it at the back, and the green dot is the limb position. Here you have the terminator. So we're going to start in the night side and go into the day side. So this was in, where were we? This was actually one of the very first orbits we did, where we're allowed to take data, so in December, 4th of December. This is just some counts that was used for checking that we're doing the exposure okay and not overexposing and things like that. So what you're going to see, the image resolution is pretty good. We expect the strengths, signal strengths we got. We're going to see lots of structures. We're going to see a little bit of stray light on the corner here on one of these channels. We're going to see the South Atlantic anomaly. You will see it. You will see some aurora at high latitudes, and you will see some hot pixels. I don't know why Ola Martin wrote this one. Dominated, I wouldn't say, but there are some hot pixels in the night glow data. You don't see them in the day glow because it's so much stronger. Okay, so let's try to get that one. Tuesday is today, and we're going to look at this one. So, and it's starting. Okay, so we're coming down here as we went. You might have seen already. We flew through the terminators. This is daytime emissions going down over the southern pole here. You see the structures. You see it. Now lots of things sort of coming into the foreground. Here's the South Atlantic anomaly coming for you. So we're getting whacked by the. This is the nice. We'll see it a second time. There's some aurora that went through as we went into the night on the northern hemisphere. There's some more aurora. We're coming now back down again. This is sort of as we go across the terminator, as we're going from the dark into the light again. You see a little bit of the banding here. This is the flat fielding that hasn't been applied yet. These pixels are binned. This is not purely raw data. They're slightly binned in order to keep with our thing. Here we have the South Atlantic anomaly again. You see the scale is actually changing all the time. So this is when we're going from the day to the night. The scale will change by about a factor of 10 or so. There's the sort of hot pixels you can see. Since they're binned, this is showing the sort of size of the horizontal binning. That's really only one pixel, so the whole bin is not destroyed. It's just slightly higher than the others. We have working on, how to take that away. Okay, so that's the first movie. Now we go back again to presenting. Right. So as I say, I've sort of summarized the things that we saw here. Then we go on here. So the current focus, what we're working on right now is sort of getting all of the level 1 calibration sort of up and running and correct. We actually do calibrate. We have calibrated data. I'll show some in a minute. We're still working on some artifact removals, such as away from the mic again. Artifacts removals, such as the hot pixels. We're using the moon, planets, stars, anything we can to check the pointing, calibration. We can take moon images. We only get half the moon because we only get when it's in the plane of the orbit, which with our orbit means we get half moons twice a month. This one you can see it was slightly overexposed on the limb here. We have newer versions of that. We're still working on the flat fielding. You could see some of that in the previous one. I think we've got a good handle on that now. We're getting some good results from stellar measurements as the stars move across the field of view. We're looking on the absolute and relative calibrations. I'm not happy with the ratio between the different bands at the moment. I don't think we're quite there yet, but we're still working on it. And I think now hot pixel removal, although it says still not good enough, I think now we've got a good handle on that in the last week or so after this slide was put together. Okay, yeah, here was one just to give you a feeling for it. These are stars, or points where we have seen stars in the CCD, and I say each star is actually taken on a separate occasion. These are not like one image seeing all these stars. We don't have that. We have most 2 stars in a picture at a time. So these are taken on different occasions, and then we have used a fitting routine to align the different channels to fit the stars as best as we can. You see there's still some little discrepancies here, but we're working on getting that. These are the channels, all 6 of them. And you see the UV2 channel is considerably below the others. We knew that before it was launched. It was put in a box, we weren't allowed to change it. But it still fulfills all the scientific requirements that we need. We'll get the noctilucent clouds in the UV channel at the same time as we get air glow and everything else in the other channels. So it's not a problem, but this is that. These are the center points of each of the channels. You see, they're not perfectly aligned, but we know where they are. And what in the end we do is we sort of chop out this section here of the CCDs to give us co-aligned images. So now we have another quick look video. So actually we're now putting on a regular basis, allowing for YouTube not letting us upload or whatever happens, daily images like this showing all of the channels. If you search for Matt Satellite and fiddle around a bit, you can maybe find them on YouTube. You should be able to find them on YouTube. And this is a sort of quick look that we have just to check everything's going and to look for fun things like stars flying through the field of view or things like that. Order here is infrared channel number 1, infrared channel. These are the 2 on band. This is the broadband one, but it's actually got a lower intensity because of it's a broader band, and these are per nanometer calibration, right? Don't believe this unit here. It's photons per square meter per centimeter per steradian per nanometer is the correct unit. But okay, so we have the 2 on band, the 2 background channels. The background channels you can see are binned in a larger horizontal bin than the on band ones. This is because they're just background, they're just used for correction. We have a lot of data restrictions. We only allowed one passage a day for download, so that's, we've got a few more now, but that's the thing. These are 2 UV channels. You see here it says idle. If they're stripy like that, they're not on. And this video is actually from March, so we don't April, so we don't expect any noctilucent clouds, so they're not being used. This is the nadir channel. It's only on in the night time. It's totally saturated in daytime, so we don't bother turning it on. Again, here's the map to show where we are. Now I will try to find this one. Tuesday again. This one is MATS level 1B. So, right. So it should go on. So here you can see sort of the only, in our clipped field of view, the only little piece of stray light we sometimes see is up in that corner of the IR3 channel. Okay, these change not like the other picture. They're not dynamically changing. They change from one scale to the other as we go from day to night. Again, these are now, as I say, calibrated images. The hot pixels have not been removed yet. They will be in the next version. So this is nighttime data down over the southern hemisphere. You can see the hot pixels as they do. You see the structures here as they move into the foreground. You saw a star fly through there, probably, if you were quick. It just went woof up here. This is the nadir channels now turned on in the night. What's the bad one? Okay, turning on here. You see it as we go through here. There is an artifact here you might have seen earlier. We don't know what it is. We think it's a piece of, we had some incidents there may be a bit of contamination on the lens, and we can correct for it because we have so many images, we can just take it away. What else should we see here? We should see these are the, as I said, 2 IR. These are the background channels. So these will be subtracted from this in this, and you see the sort of size of the scale on them is like an order of magnitude less than these ones here. Let's see. There's the transition from day to night again, and as we go into the night, the nadir camera will turn on. And you can see sort of the structures flying past us. And this is before we tune the observation times to the best values. I'll show some more nadir data in a moment. Okay, is there anything I forgot to say about this one? Don't think so. So we can, as I say, move on then to pause. Presenting. Okay. And I said these are available more or less daily on the thing. I have been playing a little bit doing some sort of first 1D inversions. Fortunately, I picked one when we're in the middle of the South Atlantic anomaly, so you see a lot of little dots on here. This was the sort of limb measurement radiance, just on the center pixels of one of the channels, and this was just inverting it to a sort of limb image, again around the equator here. So we're going from 40 south to 30 north in this particular scan here. So this is what we're aiming for, is not just to do these one-dimensional inversions, because you can see here these sort of structures you see that are these drop, like a bright spot here gives rise to a sort of an arc of intensity, which doesn't go away completely if you do a one-dimensional inversion, but with the two-dimensional inversions or three-dimensional inversions, which we're intending to do, then it will take it away. So as I said, to get rid of those sort of structures, we're aiming to do tomographic retrievals of the A-band and the noctilucent clouds. And it's working on the principle as we move ahead in the orbit, we see through the same area several times with different lines of sight. And this was a test retrieval done in a noctilucent cloud that was sort of done using just simulated data long before MATS went up. And you can see we can get this sort of cross-track structure and the long track structure. And you still see there's still some signs in this one of the sort of lines of sight. But this is what we're hoping to do for all of the channels, having corrected for background and hot pixels, etc., etc. And they will be used then to estimate temperature fields using the background, using the two infrared channels. And then in parallel with this, we're working together with the people in ULISH, looking at how you can use this data to extract gravity wave momentum fluxes. So this is some formula from ARN 2004. If we have the temperature fields, which we hope we will have from the A-band things, then you can estimate wave parameters, both wavelengths, given the Brunt-Weisler frequency, the scale heights and densities. We can calculate fluxes of vertical fluxes of gravity wave momentum. And this is some test that has been done using simulated MATS data, sort of simulated using a background model, this high ACM model in ULISH, and then trying to catch the waves and fit them and derive the gravity wave fluxes. And the true values are the ones that are derived directly from the model itself in the black, and the red is what we think we would get if we had proper MATS data. So we're working toward that. We see here we can reproduce the zonal, which is the one shown, and even the meridional gravity wave momentum fluxes quite well in this altitude region between 80 and 100 kilometers or so. And this is work being done by Björn Linder, which is one of the students there. Just as a little sample of the nadir data. So this is the nadir camera, just plotted as stripes here, and they're just plotted in time order, so they're overlapping. They're not in any way merged with one another. And what you can see is, like here we can see bits of the auroral oval as we're going over the northern hemisphere. You can see, if you get close, which you can't, lots of little structures in here, in probably the night glow part of it, but there's a lot of aurora in this part as well. But we're seeing when the sun is not high enough, we actually do see the ground sometimes. So, and we can see city lights sometimes as well. So we have to work on that as well. So this is coverage of the nadir. One will vary by season since we're only on at night. So at the moment we would be looking at the southern hemisphere. We're moving daytime. Northern hemisphere is more or less all in daytime for us in our orbit at the moment. Okay, data availability. So the commissioning phase was from 4th of November until about the middle of December. We started initial operations after the 10th of December. We were running 12 hours a day then, and we got into nominal operations from this second, or from the 10th of February here. There's still some downlaps because of limited some gaps due to downlink budget, but we've now negotiated with the people paying, and we're getting some extra downlinks, so we will not have those data yet. So far we've over 2 million images, so it's starting to take time just to sort through them. We have, as I say, the quick looks publicly available on the YouTube channel. We're hoping to have some early access release after the summer, and a more public release in the first quarter of next year. If you're interested in accessing the data early, please contact the PI, Jürgen Bull, at that address, and he will keep you on to date what applies for that. It says demographic data early access next year, or later this year. Well, we'll see. Should be, maybe. Anyway, so summary. Yes. So, MATS was successfully launched in November. Initial operations, nominal operations from February. Instrument is working as planned. Current focus is getting a good calibrated data set, which we hope we'll release in the autumn. And we're doing work now on the retrievals. Unfortunately, about a week ago, we had some problems with the reaction wheel on the satellite, so we're currently actually in safe mode, unless somebody tells me something else today. They think they know what the problem is. They're working on a get around for it. I hope we're back in operation next week, but they have to put up some patches, and they want to test everything before they send it up to the satellite. That's me. Thank you.